Hi everyone, and welcome back. In this lecture, we'll look at the root mean square error. In the previous lecture, we briefly mentioned what the root mean square error is, and it's one of the methods that we use to see how well our linear regression model did. Okay, and we want this root mean square error to be as low as possible. So the lower your root mean square error is, the better your model predicts compared to the actual price. Okay, so in this example, the blue data points represent the actual price of your, for instance, housing data, and the red line indicates your model, your linear regression model. And what we do is we calculate the distance of each data point from your regression line, and then we take the difference, the distance between your data point and then your line. And then if you square that and take the mean, that will be your mean squared error. And then the root mean squared error, we said, is the square root of your mean squared error. So you can read more about that here on Wikipedia. I just wanted to give you a brief overview of what a root mean square error is. For us, scikit-learn has a library known as matrix, and this matrix has a method known as the mean square error method, and we can use that to find out the mean squared error, and later we'll take the square root of the mean square error to find the root mean squared error. Let's see how we can do that. So first we need to import matrix from scikit-learn. So from sklearn, let's import matrix. And once we import matrix, we can simply call the mean square error method. So mean underscore square underscore error. And then this mean square error method accepts two values, which are your actual and then your actual price and your prediction. So the actual price, we say that it's y test, whereas our prediction is our prediction that we came up with from our model. Okay, so if we run this, so this is mean squared error. Let's run this again. So this is your mean square error. Okay, so we can save this in a variable called mean squared mean underscore squared underscore error. So this will be our mean squared error. Okay, and our root mean square error will be the square root of our mean square error. So NumPy has a method called square root. We can use that to calculate the square root of our mean square error, and that will give us 247,262. So that will be our root mean square error. Root mean square error, RMSE. Okay, so using our linear regression model, the root mean square error is this much, this amount. And for that we used, if you remember, we used 10 features, right? So if I go back, here are the features that we used. We used 10 features. Great. What we can do next is we can build another linear regression model with different features and calculate the root mean square error, and we can compare our two models. Okay, if you remember, these are the 10 features that we used for our first model, and for our second model, let's consider fewer features. For instance, let's consider number of bedrooms, bathrooms, square living, square lot, year built, and zip code. So let's remove some other features. So let's build another model with these fewer features. So for features, we'll only consider bedrooms, bathrooms, square living, square lot, year built and zip code. And our target, of course, is the house price. Okay. So what we'll do next is split our dataset using the train test split method. We'll use that to split the dataset into training sets and then testing datasets. So we can say X train, X test, Y train and Y test, Y train, Y test, and we'll use the train test split method. Train underscore test underscore split, and then we'll pass our X and Y. So those are our target and then our features and target. And we mentioned we can pass the optional test size attribute. So we'll use the same 30%. So 70-30 split, which is 70% for training and then 30% for testing. Okay. And then a random state of what did we use last time? 7. So as I mentioned, this random state is, if you use the same random state, you'll get the same values that I get. But feel free to use any other random state if you want. But if you want to get the same result as me, you can use this random state of 7. So once we split our datasets into training and then testing set, the next thing we need to do is instantiate our linear regression model, and I will save it in a variable called model2. We have linear regression, and once we instantiate our model, we'll use the fit method to train our model with the training dataset. Okay, so model2 dot fit, and then we'll pass our training dataset, which are X train and then Y train, right? And then once we train our model with the training dataset, we can predict by using the testing dataset, the X test dataset. So we can say model2 dot predict, that's the method, model2 dot predict, and then pass our X test dataset, and we'll save this in a variable called prediction2, since we have prediction already. And if you remember, in the previous lecture we calculated the price, the actual price, and the prediction of one of the houses, which is ID this. So that's row index 1. So similarly, if I say prediction to row index 1, so this is the prediction for that house, 718,000, using our model 2, whereas model 1 predicts as follows: prediction index 1, our model 1 predicted 724,000, whereas the actual price of the house is house 1 index the price. So this is the actual price, right? This is the actual price of the house. And what I want to show you next is calculate the root mean square error for our second model and compare that value to our first model. Okay, so to calculate the root mean square error, we have already imported the matrix, so we can simply call the mean squared error method mean underscore squared underscore error, and then we'll pass our Y test and then our prediction 2, and we can save this in a variable called mean underscore square underscore error 2, and we can simply take the square root of this mean square error 2 value and save it in a variable called root mean square error 2 is equal to np dot square root, and then pass your mean square error 2 value. Okay, if we run this and call root mean square error 2, we see that our root mean square error 2 is 248,257. Root mean square error 1 is, using our first model, we saw that the root mean square error value is 247,262, whereas using our second model, the root mean square error value is 248,257. And we mentioned that we want the root mean square error to be as low or as minimum as possible. So looking at these two root mean square error values, we can say that our first model predicts better compared to our second model based on the root mean square error, since the root mean square error value for our first model is lower than the root mean square error value for the second model. Okay, so one reason could be, remember, the features that we used for our first model are 10 features, right? We used 10 features, so more features are used, whereas in our second model we only considered 6 features, right? So the more features that you include, the better the prediction will be for your model, because as we saw earlier, we can use the coefficient method to see the effect of each of the feature on your target price, right? We saw that in the previous lecture. We calculated the coefficient for our first model and saw the effect of each of the features on the price. We mentioned that if we take, let's say, one of these features, and if you keep all the other features constant, we can say that, an increase, for instance, this could be, I just said, in literature you'll find the term unit. So 1 unit increase in that specific feature will result in this much amount increase in your target price, for instance. So you can use the same coefficient method to calculate the coefficient for the 6 features, and then see what you can generalize from the coefficient values. Okay, you can do that for your second model. So that could be one reason why your first model is better than the second model. That's by looking at the root mean square error. So here, the actual price for your house 1 is 538,000, right? And your first model predicted 724,000, whereas your model 2 predicted the price to be 718,000. So for this specific, which one is closer to your actual price? So model 2 predicts the price better than your first model, right? Since that price 718,000 is closer to 538 than 724 is. So that's something to consider. Even if one model predicts the price better than the other model, it doesn't mean that model will predict the price for every single house. It means that your model 1 will predict better than your model 2 on average. Okay, that's one thing to note. Not for every single house price, but on average, your first model will predict the price better than your second model. Okay, again, remember we have how many data points here? We saw that we have 20,000 rows, right? We have 20,000 values. So basically, it's on average. On average, your model 1 predicts the price better than your model 2. Okay, that's one thing to consider. And another example, another assignment for you is you can build another model So this is an assignment for you. Build another model and consider maybe 12 or 13 or 14 features. Okay, so if we call our house.info, we saw that we have about 21 columns. So try to build another model by considering or taking more than 10 features. So for instance, ignore this ID column. You can also ignore the date column and take, for instance, price, bedroom, bathroom, square living, floor, waterfront. So take, let's say, 14 or 15 features. Okay, so build another model and consider, let's say, 14 to 16 features, and compare the root mean square error to model 1 and model 2. Okay, so we have already seen model 1 and model 2. So build another model and build another model with, let's say, 15 features, and compare the root mean square error of your model to models 1 and 2, and what can you generalize from that. Okay, so you can try that out. Okay, before we end this lecture, let me summarize what we learned in linear regression. So we mentioned that exploring our dataset and visualizing our dataset will give us a good idea about our dataset and what to look for. Okay, so those are important techniques while working with any dataset. And then we looked at our linear regression model. We considered certain features. We started by defining our features. In this example, in our model 1, we defined 10 features and our target is the house price. After that, we divided our dataset into training and then testing data. And once we did that, we used the fit method. We first instantiated our linear regression model, and then we used the fit method to train our linear regression model on the training datasets. And once we did that, we used the predict method to make some predictions. And we mentioned that we can quickly make a scatter plot and compare the prediction to the actual price. And if you see like more of a linear relationship, that means our model is good, right? If you see more of a linear relationship between your prediction and the actual price, it means your model is good. And another common method to evaluate your linear regression model is using the root mean square error. We also saw the coefficient method to see the effect of each of your feature on your target price. And later we considered another model with fewer features. So in our model 2, we used only the 6 features and compare the root mean squared error of those two models. So again, you can try out this example. You can take it as an assignment and consider 14 to 16 features and see if you can come up with the root mean square error for that model and compare it to the first two models that we saw. Great. Thank you, everyone.